Okay, I'm going to go over these slides fairly quickly. Okay, so here's the orbit of Pluto, and Pluto's orbit is the most eccentric amongst all the planetary orbits, even though Pluto is a dwarf planet now. Okay, so, and it's not very different from a circle. So, see, there's the center of the ellipse, there are the two focal points, there's the sun, and this is Pluto's orbit, and the eccentricity of Pluto's orbit is 0.25. The eccentricity of Earth's orbit is about 0.04. And you guys can go to this simulation and change the eccentricity. The eccentricity of Halley's, oh, there's the Earth's eccentricity, which is 0.02. Halley's Comet has an eccentricity of 0.97, and that's how Halley's Comet orbit looks like. And that's how most comets, the orbits of most comets are. And when they come real close to the Earth, I mean to the sun, that's when you can see them. Okay. Okay, Kepler's second law, which states that the planet sweeps out equal areas in equal time intervals. So if this was the area swept out by a planet in a week, another week it'll sweep out the same area. Okay. This law, so here the rate at which the area swept out is constant is what Mr. Kepler said. What Mr. Kepler didn't realize was that that was a result of the fact that angular momentum is constant. Okay, so it's a consequence of conservation of angular momentum. The gravitational force on the planet, the force is central, and so it exerts zero torque on the object, and so angular momentum is conserved. Okay. So you saw that from one of the previous chapters, that external torque is equal to rate of change of angular momentum. Okay. So on a planet, the only force acting is this force of the sun, and this force has zero torque. Torque is zero, and so the angular momentum of the planet remains constant. Okay. So again, Kepler's second law. So here's this planet going around the sun, and these are equal time intervals, and all these areas are equal. Okay, so that's what this equation says. Area dA by dt, dA by dt, the time in which this area is swept, is constant. Okay, so Kepler's third law. So we'll do it for a circular orbit. Here's a planet going in a circular orbit. The centripetal force is provided by the gravitational force. So there's the gravitational force is equal to the centripetal force, and you can rearrange these terms, and what you find is velocity is 2 pi r over t. T is the period, the time it takes for the planet to go around. And so t squared by r cubed is 4 pi squared by g times the mass of the central object, which is the sun. Okay, so I urge you guys to do this. So here's an interesting fact. So for Earth, the period is 1 year. So we know t, and we've known the Earth-Sun distance for a long time. The Earth-Sun distance is 1. Earth-Sun distance is 1.5 times. Hello? Who was writing that? Okay, so the Earth-Sun distance is 1.5 times 10 to the 6 kilometers, 10 to the 9 meters. Okay, so this distance was known for quite some time. So we know the period of the Earth, we know the Earth's sun distance, and so from given these two facts. Okay, one. One year. Okay. All right. So here's Kepler's law. What Mr. Kepler said was Kepler's third law states that T squared by R. You can calculate this ratio for all planets, and since the central object is the same, it should work out to be the same constant for all objects. Now Kepler didn't know this formula. All he knew was the period for. He knew the period for various planets and their distances, and he just calculated this ratio, and what he found was this was constant. Okay, and see, this is what he found for various planets. T squared by R cube is what he calculated for various planets, and these are the numbers he came up with. Okay, he didn't know why this was so. All right, so again, like I said, you guys can calculate the mass of the sun at home. Just use, so from Kepler's third law, use the period of the Earth and the Earth-Sun distance, put those numbers, and you can calculate the mass of the sun. And the mass of the sun, here's the notation for the mass of the sun, is 2 times 10 to the 30 kgs. That's what it should come out to. Okay. I suggest you guys try it. Okay, so in today's world, we depend on satellites quite a bit. You guys all are reliant on your GPS navigation. And those GPS satellites, by the way, are fly about 12,000 miles above the surface of the Earth. And there's roughly about 36 of these satellites flying around. So there's a constellation of those satellites. Okay, so so the orbital speed of the satellite around the Earth is given by gm, okay, or the orbital speed of any object going around orbiting a heavy mass. The orbital speed is given by g times the mass of the central object divided by the distance at which you're orbiting. So the further out you are, the slower your orbital speed. Okay. So, and the orbital speed falls off as 1 over r to the power half. So if you're 4 times as far, your orbital speed is half as much. Okay, so that's what that equation is telling you. So that's the orbital speed of the satellite. Here's a very interesting idea as geosynchronous satellite. So imagine now in this picture, that's not the equator, but let's say that was the equator and this was the North Pole. It's not the North Pole. You can see the Africa there. Okay, now the Earth rotates once in 24 hours. So if you could find a satellite, if you could find an orbit such that the orbit takes 24 hours to go around, if you're going in the same direction, spinning in the same direction as the Earth, and you're doing this at the equator, what you'll find is you'll be about the same spot on the Earth, and that is called a geosynchronous satellite. And it turns out that for a geosynchronous satellite, the radius, orbital radius is 42,000 kilometers. The radius of the Earth is 6,000 kilometers. So that's 36,000 kilometers above the surface of the Earth. And the orbital speed is 3 kilometers per second. Okay, so again, a geosynchronous satellite orbit is very important. So let's do this. So here's the Earth, here's the North Pole. Okay, so if you're looking from above the North Pole, and here's a geosynchronous orbit. So the radius of the Earth, there's the radius of the Earth. The radius of the Earth is 6,400 kilometers. And this radius is 42,000 kilometers. Okay. And so there's the equator. This satellite, which is going at about 3 kilometers a second, it'll stay right about that same spot, because this is taking, this guy is taking 24 hours to go around, and this guy is going 24 hours. Now, remember, if this guy were going in this direction, he won't remain on the same spot. And you can go orbit at 42,000 kilometers. If you were going above the North Pole, again, you wouldn't be in a geosynchronous satellite. So it has to be in the equatorial plane and has to be going in the same direction as the Earth. And this is a very useful orbit for communication purposes, because since he remains on the same spot, you can bounce off signal, okay? And so these parking slots are the most expensive parking slots. Okay, it turns out that just because of technology, you can park satellites half a degree apart. Okay. So since there are 360 degrees, there are 720 of these parking slots for geostationary satellites. And those are the most expensive parking slots on Earth. Okay. All right, so that's the geosynchronous orbit. Okay, so here's a satellite. Now the satellite is bound to Earth because it's not running away. And the energy of the satellite is kinetic energy plus potential energy of the satellite. And since it's bound, this total energy of the satellite is less than 0. Okay. And it turns out that for circular orbits, anyway, you can show that the total energy turns out to be minus GMM by 2R. Okay, the kinetic energy is half the potential energy, half the absolute value of the potential energy, and that's what it turns out to be for circular orbits. For elliptical orbits, the total energy can be shown to be that. Okay, we are going to pause for a second, take a